Okay. So are you ready, Russ?
Yeah.
Okay, so we have the pleasure today of having Dr. Russ Horn with us from the University of Luxembourg, who will be discussing how bisimilarity, which is a concept inherited from operator algebra, formal semantic of concurrency, actually was a key tool in his discovery of a vulnerability in ePassports. So if you'll take it from here, Russ, thank you very much for being with us today.
Great. Thank you very much for the introduction, Clément. So this is quite nice to talk at Augusta, even if it's virtually, because over the past few years, I've had a few very nice chats with both Harley and Clément about topics which we have in common. So Augusta is a natural place to be talking to. So in fact, with Harley, we've been talking a bit about attack trees, which we can give like a logical semantics for kind of comparing different attack scenarios and things like this. And in fact, we've actually done a bit of attack tree analysis of passport vulnerabilities. So this is a nice little case study, which triggers some non-trivial aspects of attack defense trees. But I'm not going to talk about that today. Maybe that's a talk which is around the corner. So today I'm going to focus on basically the role of process equivalences in analyzing privacy properties. And this is related to a conversation I've been having with Clément, which is essentially because there are different equivalences, you can specify privacy properties using different types of behavioral equivalences, and they have different expressive powers. This kind of has an implication for like the testing capabilities, and the testing capabilities really in this kind of security setting correspond to basically the things that the attacker can do to interact with the system. So you have like the system, which is a protocol which is running, and the attackers there trying to interact with the system. They're essentially testing it in some kind of way. And these different games that you can play when you are trying to intercept inputs and outputs in a protocol and induce certain behaviors, these essentially describe the kind of strategies which is essentially an attacker might be able to follow in order to kind of like maybe distinguish one user from another user, and thereby perhaps basically violate the privacy of the individual. So equivalences have become quite an important tool there, but what's been less explored is what does it mean to choose one equivalence over another equivalence, and what happens when, for instance, you have an attack which holds according to one equivalence, but does not hold according to another equivalence. How do you interpret that scenario? And essentially, that's got to somehow be some kind of way of, you need some kind of way of basically mapping the kind of semantics of the equivalences onto like what that means for the capability of an attacker. So this is an ongoing line of research, but I'm going to report on what we've done so far. And along the way, maybe I'm going to kind of just point to like, here, there is something interesting that we could look at. I hope this is the beginning of discussion with Augusta University on the topic. One thing I heard there's several students attending potentially. Is it master students mainly?
Right now, we have a variety of students fairly close to graduating, from PhD students and three faculty members.
Okay, so there's a few graduate students. So don't worry about this if your thesis or whatever is not in the area of bisimilarity or even privacy. I'll keep things at a reasonably high level and explain the details, less so and more so the kind of concepts. Okay.
Thank you very much.
Great. So this is something fairly understandable. Okay. Now, imagine you have essentially, and this is the kind of privacy scenario which I'm going to focus on for this talk, is this concept of unlinkability inside passport systems. And essentially, when you're using a passport, so this is say this is a passport here, okay, inside your passport, embedded inside, usually inside the kind of photo page, inside there's an antenna which runs around the outside, and there's a little chip inside it as well, a little RFID chip. It's like a kind of just no bigger than the end of a pencil, I think, and it has about the power of a kind of 1980s PC inside that. And what you do when you want to communicate with that chip is you present the passport to a reader, okay, and what happens then is it reads a key, which is printed on the biometric page of this passport. And so it doesn't actually read the passport, it just reads the key, and then it communicates with the chip using the antennae. That's what the reader does wirelessly, to transmit information, including like your name and expiry date and so on, but also maybe some biometrics, for instance, your fingerprints. That allows you to then enter through the system. So the fingerprints are being taken from the ePassport. They don't need to contact some central database. It's all stored inside that chip inside your passport. So these are the biometric passports. And a typical thing you might do is you might be walking around the terminal and you might go to, let's say, an automated ticket issuing service, like this is offered by the airline. You go there, you present your passport now, and often it can just automatically give you your ticket, your boarding pass, without having to go in queue. So that's something that's maybe offered. So you present your passport there, and then later on you go through and you've got a checkpoint where you need to pass through an international border, and you have to present your passport again. And sometimes this is automated again. There's automated checkpoints. So each time you're doing this, you're executing a protocol, which is wireless communication. So typically, this is a typical scenario you have, is that you have one ePassport here, which is the one you hold, and maybe you have a session with one ePassport reader. This is the ePassport reader, and then you move on, and then you have another session with another ePassport reader. That's a typical thing you might do. You don't have an ePassport, use it once, and then throw it in the bin. You use it multiple times, so that you can have one session with multiple readers. Okay. But ideally, if someone observing you in the outside, someone who's like snooping in all your wireless communications between the readers and passports, so they could have a device like several meters away, which is strong enough to kind of pick up on all the RFID signals, they shouldn't, from that information that they gather, be able to then say, that's the same person that I saw before. I know that this person was here, and I know this person went there, and afterwards they left the country through this door. So this is a kind of a problem for traceability. Maybe you don't know who it is. Maybe you can't read the passport. Maybe you can't obtain the fingerprint. Maybe you still got some kind of decent level of security. But by exploiting the protocol, you can use the protocol essentially to track people. This is an undesirable situation, and indeed it's written into the standard that for like the kind of the requirements of passports, that this kind of untraceability or unlinkability should hold for passports. So ideally, what it looks like, if you were to really design a system so that truly nobody could be tracked, then you have a passport, you use it with one reader, okay? Use it once, and then you throw it away. And then the next checkpoint, you have another passport, which has a new identity, and you use it once and use it with a new reader. So you never use the same passport with two readers. You always use it once and then you stop using it. You never use it again. And clearly, if you took a passport, you threw it away in the bin and never used it again, you can't be traced to the next movement. So ideally, what we're saying here really is if a system satisfies this unlinkability property, then clearly the system, which remembers this one here, the system here, where people can use the same ePassport across multiple readers, should appear to be the same from the perspective of an attacker, an observer snooping on the wireless communications, to a system where essentially each time you have a passport, you use it once for each reader. Okay? This is a scenario. And if we can say that they're equivalent, that's what the symbol here is. If we say that they're equivalent, the system and the specification of what the system should appear to be like, then we can say, look, clearly it's impossible because there was no movement of the individual in the specification. Clearly, therefore, the attacker cannot mount an attack on the system where the attack would allow them to kind of re-identify someone at a later checkpoint who's holding the same passport. Okay, so this is how we might specify unlinkability as an equivalence problem. Okay, and the counterpoint to an equivalence problem is if you have basically an equivalence between two processes. Essentially, each protocol is a process. So the specification and the system, the real system, how it behaves, the idealized specification of how it should behave, these two things are processes, and they are process equivalent according to the previous thing. If they're not equivalent, however, then that means that essentially there is some kind of strategy which the attacker can do, which it can perform in one of the either the specification or the system, but you cannot do in the other, and that essentially gives you an attack strategy. Okay, so this is a kind of, if people know category theory a bit, I know there is, I don't need to talk about category theory much, there's this concept of stone duality. So there's a stone duality between the equivalence and this modal logic, which essentially is characterizing these attacks, essentially between the attacks for the system and these equivalences. So I'll explain that a little bit more. So whenever we have that two processes are not equivalent, we can come up with a formula, and this is a formula in some kind of modal logic, which holds for one thing, which is in this case, the system, where the same passport has been used twice, but does not hold for this other system. And this modal logic formula essentially gives you, it tells you what the attack strategy is. So we're going to see examples of this. Okay, but this is the general methodology we're going to appeal to. Is like something which has been developed, I mean, for like 30, 40 years in the process algebra community. It's the idea of a Hennessy-Milner logic, which characterizes an equivalence, a behavioral equivalence between processes. And here we're exploiting it in the security setting to essentially either prove something using the equivalence. So if we have a proof, then we can essentially prove this equivalence relation. And if there's an attack, what we can do is we can do the following. We can exhibit some kind of formula which represents it or describes the attack on the system. And there's no middle ground. So either we can do one or we can do the other. There's a soundness, a completeness result here. Okay. So, but then I said equivalence in a kind of very vague sense earlier, and does this notion of equivalence matter? And I was hinting earlier, before I started going through the slides, that in fact this is part of the crux of the matter, is that, well, there are many different process equivalences and they have different expressive powers, and each of them therefore corresponds to different attacker capabilities, and which ones are good ones to use, and what does it mean if it holds for one but it doesn't hold for another? And this is the kind of question which has not been asked really before, before we started studying this particular attack. And the reason why it's quite interesting for this attack is most attacks, it's very clear, like all equivalence we'd be able to find it, or all equivalences we'd be able to disprove it. But this ePassport scenario is a kind of fishy one. It's one that you can really argue about for a long time, maybe forever, about what you think is the right equivalence to use. And this has been going on for about at least 10 years. So this really matters which equivalence it is. So we go back 10 years, we find the story here. So about 2010, this is when the first formulation of unlinkability for ePassports was made in terms of a process equivalence, in terms of bisimilarity. This is equivalence used here. This is a very nice paper. They come up with an attack on the French ePassports. They explain it in terms of process calculi, and it really is an attack. It's something which was it's very practical to exploit to re-identify people. So it's a serious issue which was discovered using this kind of methodology back in 2010. But they made another claim. That was for the French ePassport. They claimed that the UK ePassport, which is has a kind of like slightly better implementation, and most ePassports now are like the UK one, that one in fact did not have a flaw. So, and they actually claimed to have a proof. So here's the thing here. Sorry, wrong highlighter. This one here. Nope, highlighter doesn't want to be highlighted. They claim to actually have a proof of unlinkability of a particular protocol used inside ePassports. Okay, but it turns out that they didn't provide a proof for it. So they claimed to have the proof, and it turned out they used a tool, and inside the tool there was a bug. So the tool said yes, there is a proof, but in fact later on they found that there was a bug, and of course that invalidated the proof, and so therefore it became an open problem. The story goes on. 2012, there was a false attack discovered using another tool in Vincent Cheval's thesis. What do I mean by a false attack? Well, it's an attack according to the tool, but it's just because the tool was using a slightly wrong semantics or out-of-date semantics for choices inside the system. So that wasn't valid. It was a spurious attack, we call them. The attacks which the equivalence gives, but are not really exploitable in any way. They don't really mean anything. Then 2014, he improved a tool. APTE was a tool which is based on his work. And he ran it. You could run it for like several days, and it would give you no answer. It would neither prove it nor disprove it. And this kind of indicates that this is a difficult problem. As you have a tool which is really crunching it just for 2 sessions, and not even for like infinitely many or unboundedly many sessions between ePassports, just for 2 readers, and already was timing out. Okay. 2016, this is where we start to see another side of the story, is that there was a proof now of weak unlinkability, which was established. Now, there's a difference between strong unlinkability and weak unlinkability. This is using strong bisimilation. This is strong here. So you use bisimilation to prove the property, and with weak unlinkability is a trace property. Okay, and in fact they use trace equivalence. So their proof essentially applied weak unlinkability, which is in terms of traces, but not strong unlinkability, which is in terms of bisimilarity. Now, for people who don't know what the difference between trace equivalence and bisimilarity are, essentially with the trace equivalence, what you do is you decide everything you're going to do at the beginning. So you say, I'm going to do this, that, this, and you have a sequence of actions, and you say at the beginning of what you're going to do, all of the things you're going to do in a sequence. Whereas with bisimilarity, what you can do, the extra power you can have is you can make choices in between. You can if you have you can wait to see what happens, and then at a certain point of the protocol, you've got to say, for instance, 2 inputs. You could take this input or you could take this input. You can make the choice, and you can make that more dynamically, so it becomes like a game. And this gives you more expressive power. So although they have this proof in 2016 of weak unlinkability, this doesn't mean that we have a proof of unlinkability. So this original claim remains open, basically. 2018, there was another attack found in this protocol, and this was using a slightly different formulation of the problem. And here, I'm going to draw attention to my first kind of thing I want to highlight to Clément in particular, is that the way they formulated it differently they were able to find this attack using trace equivalence. But the thing is, the question is whether there was a trace which was really an attack. Okay, so what I mean by that is that we have a system in a specification, and we had a trace which holds for the specification, which, remember, it only allows the same ePassport to be used once. So you can never use it again in another session. So you can't trace people in the specification. This is an idealized viewpoint. Okay, so there's a trace for that. So that means you can determine whether it's a different ePassport. So there's an attack trace which tells you when a different ePassport has appeared. But there's no attack trace which tells you when you have seen the same ePassport. So there's no trace on the other side of the system. But if we change the equivalence again, if we don't use trace equivalence, if we use something like POMSET traces, then we get an attack the other way. So actually this you can change the semantics slightly. You can move into something called the true concurrency field, and then you can start to find new attacks using their formulation. So that's quite interesting in itself, and that's something to get into detail, but that's not what this talk is about, and that's something for future. And then we move on to where basically the contribution of myself and some students and Xiaoke Mao, who's a professor here in Luxembourg. What we observed is that essentially that it was actually using some kind of new technology which had developed in Singapore for reasoning about bisimulation of cryptographic protocols, basically better techniques for essentially proving the bisimulation methods. It was actually really easy to find an attack on strong unlinkabilities. Once you got the method, which was the difficult bit, you had to improve the technology, the actual theory. Then if you applied the theory to this particular problem, then almost straight away it just gave you like systematically an attack. And this attack invalidates the original one. So this is in fact not true. There was never a proof in the first place. We have basically a counterexample to this, and the counterexample is this modal logic formula, which I described earlier. And that modal logic formula essentially describes a real attack which can be exploited for this problem of tracking individuals who are holding ePassports. So I want to explain that formula a little bit, and that's so this is the kind of background leading in. And now I can get into a little bit of detail. There's probably too much to take in entirely, but I'll try my best to explain. So just slow me down if I go too fast at this point, and ask questions. So firstly, like, to give a feel of what the protocol is like, I need to maybe kind of describe it a little bit more. So this is a MSC diagram for this BAT protocol. The BAT protocol is a basic access control protocol, I think it is. And this is essentially an authentication protocol. What is an authentication protocol? Well, an authentication protocol is basically something that's really important to run at the beginning of a communication. It checks you're really talking to the person you think it is. So like, for instance, if you are trying to contact a website and you think it's Google, but in fact it's not, it's some attacker, then that's a bad thing. So it could be a fake web page. So you need to authenticate who you're talking to at the beginning. This is always done in most protocols. And of course, ePassport is no exception. Basically, the reader needs to know it's really talking to the ePassport that is just read the page of, and it's not read the page of one ePassport and it's talking to another ePassport, or a malicious individual inserting fake fingerprints or whatever. And vice versa. So the ePassport needs to know it's really talking to the reader, which is really in front of it, that it just was laid down on top of, and it's not, in fact, thinks it's talking to the reader here, but it's in fact talking to someone else. So this is why you run an authentication protocol at the beginning. And the protocol works by, first, when you present the ePassport, And this dotted line is actually not a kind of wireless session. This is basically what I was discussing earlier about the OCR session, where you actually read the front page of the passport and you find some keys, and these keys are going to be used for encryption, basically. These keys are unique to the ePassport, so you know that things encrypted using the ePassport keys come from this ePassport. And then the reader basically challenges the passport. They say, okay, in order to initiate the protocol, after saying the reader saying, okay, are you an ePassport? It will say, yes, I am, and here's a nonce. A nonce is something randomly generated. It's just a completely random number, but one with good cryptographic properties, so you can't guess what it is. And the reader then generates his own nonces, let's say NR, encrypts it along with the thing which it received, which should be NT. Okay, I put NT prime here because it could potentially respond with something else. It sends us back to the passport, and it checks, for instance, whether NT, which is the thing which was sent initially, is exactly the same as NT prime, which is the thing which was sent back by the passport. So that's checking that the reader really received this nonce NT. And this then, in the next response, when the ePassport sends something back, what it's doing is taking the thing NR, which was generated by the reader, and it sends it back to it sends it back to the reader to prove that, so the ePassport essentially is proving it's received something. And at the end of this protocol, you establish a key, and then a shared key, and you start transmitting things like fingerprints. Okay, so this is the basics of the protocol in an MSE diagram. And we can model these kind of MSE diagrams. So what we do is essentially you can look down, basically, let's say, I can look here, just at the ePassports, things I see, like, well, I'm going to receive something, then I'm going to send something, then I'm going to receive something, then I'm going to do some checks, and then I'm going to either send an error message here, or I'm going to send some other response. So you can basically project down each of these strands of the MSE diagram, and you can come up with a process which models basically the behavior of the passport and the behavior of the reader. That's what these two processes are. And I don't want to get into the syntax here, because this is too much to consume if you're not familiar with process calculi. But essentially in here, you've got things like, this is a send operation, this is a receive operation, this is a checking that two messages are the same, this is generating a nonce. So inside the PyCalculus, which we're using here, you have all the kind of machinery to describe these sending and receiving of messages, of which happen inside the protocol. Okay, and these are all happening, remember, wirelessly, so you can basically intercept them on the air if you're in the vicinity. So performing inputs maliciously is a little bit more difficult, but reading things is really easy.
Can I ask you a question?
Yes, absolutely.
So I'm not very familiar with authentication protocol. Is this one any particular with any respect compared to other authentication protocol, or it's just a good one that they implemented and it's fairly generic?
I would say it's an okay one. It's an okay protocol. It has lots of flaws. It has flaws that we know about. And for that reason, in fact, the BAT protocol is now no longer recommended inside ePassports. In fact, we use something called PACE, which now uses a Diffie-Hellman handshake, which strengthens certain security properties, so particularly something called forward secrecy, which is basically, if in the future, your key is compromised, like someone learns a key and they can't go back and find where you've been in the past. This is the forward secrecy concept. Okay. So it's not brilliant in the sense that property does not hold, and it's not brilliant in the sense that the key material has a very poor entropy because it uses things like your name and I mean, it's a terrible key. So these things have been improved.
Okay.
But this is an important point: is that even if you improve this protocol, there's still an attack. So there's still this attack, which I'm describing now, is still valid on the PACE protocol.
Okay.
And so this attack is only reliant on one thing, really, and that is that at the beginning you have to establish some kind of shared secret, and that's what this presenting your passport physically to be read is. So even with the PACE protocol, you have like a 6-digit PIN somewhere, which is printed on it. You present your card, and it's just reading the 6-digit PIN. And then it is wirelessly communicating with your identity card. If you're in the EU, I don't know whether in the US you have identity cards of some sort for some purpose. Probably not, because it's maybe privacy issue. But in the EU, it's normal. But so this protocol has been used inside all sorts of e-documents. And the PACE protocol should be used, but the PACE protocol still suffers from the problem which I'm about to describe. But at least address even more serious problems. So that's good.
Okay, thank you.
So it's not the best, but it's okay. So you have this idea. You have two parties in the protocol. You can describe them, the behaviors that kind of someone who is honestly following the protocol, like a genuine reader and a genuine ePassport. You can describe their behaviors. And essentially, the attacker, who could be like someone who's manufactured a fake ePassport or a fake reader and has like some kind of like Wi-Fi set up relaying messages between the two and so on, they can do whatever they like. They can intercept as long as they can't get inside the kind of like memory state of the devices, but they can see all the communications, all the external communications. So this is the kind of testing capability that they have. And they can start to even maybe insert messages and things like this. So what we can do is, remember, I have these two systems. I have the system, which is like the situation where you can use an ePassport multiple times across multiple readers. And there's one where you just use it once and you throw it away. And that's how ideally the system should appear to be from the attacker. And then you can't tell if someone has been in the system and used things twice. So I can model the system as follows. What I do is I generate this shared key material. Okay. Sorry, this is a shared key for, in fact, transmit. This is modeling the OCR session. So this is a kind of secret channel. I don't want to get into this too much because I want to actually throw it away. It's a bad idea. But it's what was how it was originally formulated. The important thing here is that we have a reader, okay, and we have multiple readers. So if you're not familiar with process calculi, this exclamation mark means that I have a process and I make as many copies of it as I like, as I need. I can dynamically make copies forever of this. So that means basically there are as many readers in the system as you like, okay? And over here, I have this main UK, which is this ePassport process, and that is also replicated many times. But for each passport, I'm going to generate this new key material for the passport. So I have this key that I'm using for encryption and the key that I'm using for MAX. I haven't got into MAX because it's a little bit perpendicular here, but it's inside the protocol. There's a MAC key that you use. What happens here is you have if you notice the replication, this exclamation mark, it appears just in front of the ePassport. That means that you can use the ePassport as many times as you like. Each time it's going to be using the same keys, KE and KM. So that's basically allowing you to use the same ePassport over and over again, okay? And furthermore, there can be more than one ePassport in the system. So that you can have many people all using their own ePassports. And that's what this outermost exclamation means. It says, I have as many copies of the ePassports, which can be used as many times as you like, okay? And this is really modeling the situation. You have many readers, you have many users, you have the users are using the passports many times, and we don't know how many times, but we're allowing as many as you like. And that's what this process is, System UK. With Spec UK, changes it only in one symbol. There's only one difference. Can you see the difference here? So there's no exclamation mark here. You see there? In front of main UK, there's no exclamation mark. And that means, of course, we generate the identity, we generate, manufacture a new passport, which has embedded in the chip the fact that it's only going to use a particular key material for encrypting communications. We only use it once. We're not allowed to use it again. We manufacture it, we use it, and we throw it away. And as I said, that's essentially the specification system. So this is how we're modeling it inside the apply pi calculus. This is due to Arapinas in 2010, which is the paper at the top of that timeline I showed you earlier. Okay. And the theorem that we have, this is our first contribution, is to prove that in fact system UK is not equivalent to system spec. So that means that these two things are not equivalent, and therefore strong unlinkability does not hold. Okay, so that's the first theorem. Okay, but then that's by itself, that doesn't really mean anything in a sense, because you could say, okay, but you modeled it using this particular way and the apply pi calculus using this particular equivalence. What is there to say that in fact this is even a good model of the system? It might not even be a good model. Okay, so it might be that okay, you can't prove the equivalence, but that doesn't mean that there's any kind of consequences for the real world of not being able to do this. So you need to look at this and evaluate whether this is in fact something which is, let's say, practical. We can even approach this question methodologically. This is what we do. So we're using this modal logic, which I was describing earlier. So we have system UK over here. So this is one of the processes you saw. This is the one where you're remember the system is how things really behave. So passports can be used multiple times by individuals. And you have some big modal logic formula here. This is a Hensey-Milner logic formula for this particular notion of bisimilarity, which holds for the system, but does not hold for the specification. And this I'm claiming describes an attack. This is an attack in the system. So each of these formulas, they're actually not more than just one. This is just one example that we came up with. There are many formulas you could write down, which are distinguishing. None of them are much shorter than this, by the way. You kind of have to go through the protocol twice in a sense, which involves a certain number of messages. But this is essentially a description of an attack on the system. That would itself, I need to argue, I need to present more to you to convince you that. But firstly, I'd like to just very briefly explain that this, although this is a really quite complex area, the semantics of this modal logic are really simple. So we just have equality, we have conjunction, we have negation, so that's just propositional logic. And then we have this diamond modality, which means that pi is like an action, like I do an input or I do an output, okay, inside the protocol. That means that basically I'm in a state where I can do a particular output or input, and I reach a state which is going to satisfy phi, which is going to describe the rest of the kind of attack that you need to perform. And that's it. So that's your entire modal logic formula. And then you have a interpretation of what the equality means, which takes into account a bit of the kind of knowledge of the attacker at the time. You have a semantics for box, which is basically there exists a state which you can reach, which can perform the action and still satisfy it. And if you have conjunction, it's just conjunction, negation is just negation. So the semantics is really simple. This is a kind of standard semantics for this kind of logic. So it's relatively easy to understand that the theory from this angle. What's a little bit more difficult, as I said, is interpreting what this formula means. So essentially, this formula here, this big thing here, when you kind of evaluate it on on a particular process. You say, does it satisfy something or does it not satisfy it? You essentially generate a kind of a game which you play, and this is a game that is generated by this formula. So you start off in these two states at the top. These are our starting states where we have the system and the specification. And I'm going to mark using the dagger who is playing, who's going to lead in the game. So we have a game where, okay, the system has to plays an action. So it plays this action here. The specification has to match it. Okay, so it does that. The system plays an action which is performing some output. The system has to match that. Okay, this is basically starting up two sessions. Okay. Then we perform some action, which is some input, where we input get, which is basically start the protocol, get challenge. The system has to match that. Okay, so far the system has been able to play the game. At the next point, the system plays a game, so it plays an action. It says I'm going to output the V, and the specification has two choices. It can output V over here, but then that V is going to be equal to get, which is not the case here. So implicitly here we have that V is not equal to get. This is get challenge, which is basically the start protocol message. And at this point, I've put a dagger here because essentially that means we have to follow this branch. This is a branch that the specification has to follow to keep up with the game. At this point, the specification gets to choose a particular input action to perform. It's like basically which protocol which of the two readers am I going to use at this particular instance? Is it the one that I've just passed through? Is it the new one that I'm going to talk to? So essentially, the specification talks to the new one. So this is basically enforcing the choice of which reader we're going to take in the game. And the system now has to lead, and it can lead in two different ways. It can essentially start up an entirely new reader with a new passport, which is not what's going on here because we're later on in the protocol. So this branch we don't want to take, just like we didn't want to take this one. And it has only one other choice. It's forced to take this particular choice here, which is basically to continue the protocol with that second reader. Okay, then we return the game again. So the system is now leading. The system performs these three actions. Essentially, the specification has to perform these ones. These branches both end up in distinguished states. And at the end, essentially, the specification ends up with a message, which is an error message. And the system, on the other hand, ends up with a message which is not an error message, which is basically the last message in the protocol you saw, which is an encrypted message, which is basically the conclusion of the protocol. Now, this is really difficult to understand. You could sit for like several days and think about this and still not maybe agree with me that this is an attack on the protocol. But essentially, this is what that modal logic formula is giving you. It's giving you this kind of strategy where the important thing is this choice of which reader you use. Do you use the reader which you just passed through, or do you use the next reader along to actually continue the protocol? Okay, that's the important thing here. So maybe this is a little bit easier to understand what's going on. So this is a MSC diagram. This is very intuitive. I think many people who've done a bit of software engineering have seen something like this. What happens here is we take the key for the ePassport and we feed it to some reader, which is basically the one that you're just passing through. Okay, and then you let someone walk around the airport. Okay, so you start the session with the reader. You intercept the message. Okay, so you start you block the communication. So the reader is basically stuck in a state where it's ready to start the wireless session. It has the key, is ready to start the reader, and you try and block that for as long as possible. And then later on, when you're trying to re-identify someone, you can walk up to them in the terminal, and you can basically use a mobile phone or something for this kind of thing to basically take that passport and make it act like a reader. And you basically you relay the messages from the reader you passed through previously. Okay, you relay them across, and you relay them back. you perform the protocol using your mobile phone in the vicinity of someone, you relay back to the old reader and you say, yes, indeed, that was the person that I saw before, because I get at the very end, I get this thing which is not an error message. Okay, so this is the same attack again, but maybe described in a slightly more intuitive way. But you can see what's going on here, because this, I've pulled it apart a bit more, and I've made it explicit, that essentially that there are actions of the attacker. There's you've got to block communications for one passport. You've got to kind of like hold it in a certain state for a certain length of time. And then on the other hand, you've got this passport over here where you're essentially the fake passport where you're, sorry, this is in fact the reader, which you're forwarding it to the reader over here from the real passport. And this is coming back to the real ePassport. Sorry, maybe I said that, misspoke that. But anyway, the idea though is that this is something which we can implement, and indeed our students did implement it. So we have a real implementation and demonstration of this particular attack. And we sent it off to ICAO, who are the main organization, and they eventually responded through the press saying, indeed, this is an attack. So maybe I'll come to that statement. It's an attack, but not a very dangerous one compared to some of the attacks. There's some even more dangerous attacks out there. But the important thing about this is an attack on the protocol itself. So it's valid for all passports, whereas a lot of these other attacks are exploiting something about like maybe the timing of like a particular implementation of the passport. So it's like using side channels and so on. So whereas this is actually a flaw in the specification. Okay. So a little bit about, so let's say this is just an introduction to the paper which I mentioned in the abstract, which is this discovering ePassport vulnerabilities using bisimilarity. So a little bit about what's inside the paper. Essentially, I described this kind of like improvement of the notion of bisimilarity. This introduced a new notion of open bisimilarity for the apply-by calculus, which allows you to very efficiently symbolically discover these kind of attacks and explain how that works. And another thing we do is we say, well, actually, that game was a little bit difficult to understand that I've just explained to you. I'm sure you agree with that. We could actually model this in a slightly cleaner way, and we get cleaner games as well. So I want to very briefly cover that and then conclude. I think that's suitable for the time left. And for all we do, so this is still the same process representing the passport. So you just have to trust me there that this is these things model the passport and the reader, or the actions they perform. I do a couple of things. I reformulate, shuffle things around a little bit, so you can use something called strong bisimilarity instead of weak bisimilarity. And this avoids a problem called image finiteness, which basically means that at every point there's only a finite number of things that can happen for every action, which makes things a lot easier. So we reduce it to a simpler problem in that sense. And also what I introduce a particular, a fresh channel for each session, which is basically saying like, well, you can tell the difference between a passport in one location and a passport in another location, because you have to set up the communication channel with them, and you have to be in a particular location to do it. And so there's no ambiguity about who you're talking to initially. And this actually changes the expressive power of it just cleans things up and in a realistic way. So these two small changes allow us to get this much simpler game. So I hope if you didn't understand the last one, I hope you understand this one. Okay, so this is the formula. Did I give the formula there? No, but this is the same. This is basically an alternative proof of the same theorem. So what we do is we start with the system. Remember the system, you can use the same ePassport multiple times. The specification, you only get to use it once, and you have to use a new ePassport for the next session. So we start up a couple of sessions. This is basically the initialization thing that I've added. The communication starts, so the nonce is advertised. It's then the nonce is advertised for one passport. Wait a minute. So we got readers and passports. Yes, okay. So R, what that is starting a new reader. This is advertising new reader. This is advertising a new passport, okay? And then this is starting the actual protocol, okay? And what's happening over here? Well, we still set up two readers. The readers are not sensitive to who they talk to until you present them information. And then we have a choice. Either we start up a passport which talks to the first reader, or we have a passport which talks to the second reader. Okay, those are the only two possibilities for the specification. But in the system, you make a particular choice, and then you go ahead, and you have a choice here. There's no change or play in this one. This is just a simulation game. It's not a bisimulation game. It's just simulation is enough here. We get to choose whether we're going to take the output from the passport, whether we're going to feed it to one passport or whether we're going to feed it to passport reader or the other one, okay? And over at the other side, you've already made that decision because you already decided that earlier. You had to decide earlier which passport you were talking to, because you didn't have the luxury of starting up two readers that both talk to you. You couldn't choose later. You had to choose out straight away. So the point where you choose differs. And then you can bash ahead just with protocol, and there's nothing you can do. And if you choose this branch, then if basically the specification takes this branch, you take this branch. If the specification takes this branch over here, then you take this branch over here, and you always end up with a difference at the end. So you end up with a difference over here or a difference over here. So it's a distinguishing strategy using something called simulation, which is just a one-sided, like cut-down version of this bisimulation I was talking about earlier. Which uses less capabilities. In fact, there's kind of probabilistic testing scenarios for this stuff. So that gives rise to all sorts of possibilities for interpreting what the attacks mean and what they mean in terms of testing, because testing capabilities were lower, which means it's an easier attack potentially to implement. Maybe there's other strategies I haven't even thought about exploiting this. So this is interesting. We're moving from one equivalence to the other. This is a weaker equivalence, which will find less attacks, but still we can find an attack. Okay, but if we go too weak, remember, if we go to trace equivalence, we can't find an attack. So it's how far up can we go? It seems simulation is a good place to go. Another place would be POM set traces. That's another thing we want to discuss. Okay, that's the formula for this strategy. Remember, I said that these game diagrams are generated from a Modal logic formula. That's essentially the formula there. And I think I'll move to conclude. So what are the lessons here? Well, we should avoid these mistakes. And this is you can't have things which are deployed across hundreds of countries, like with a billion users, and then 10 years later find there's a flaw in it. And have false proofs. So we need to do better with the methodologies here. So it's important. This is a significant contribution potentially if we can improve the methods for proving bisimilarities and for finding attacks and for interpreting them. So this methodology needs to be improved. So what we did is, just to recap, we reduced this strong. We reduced the unlinkability problem to the strong bisimilarity problem. We then use something called open bisimilarity, which is explained in the paper. It was way too complicated to explain here, to quickly and systematically find the attacks. So this is a new methodology. And then we used a modal logic to basically check whether this is a real attack. So you can come up with open bisimilarity, come up with things which are not really attacks, but then you try and construct the modal logic formula, and if you succeed, then you know it's an attack. And then you can start interpreting it, because it's again, you're moving from a kind of weaker equivalence to a stronger equivalence to verify, in fact, it's an attack in the stronger equivalence. And effectively, you have a game here between different equivalences. That's interesting. And there's something else which is like kind of like ongoing work. So a student, Simeon Yurkov, I think he might be listening via YouTube. He's been working on some other protocols, like basically these e-payment protocols. And there he's using something called quasi-open bisimilarity, which is useful when you only get a fragment of the system, or you want to prove things using a fragment of the system, like an open system, and you want to basically you need to make use of a congruence to establish this property efficiently. Well, you don't need to. You could you spend a lot of work proving it for the whole system, but it's much nicer to just talk about the small part of the system. And for this quasi-open bisimilarity is good. But this changes again the testing capabilities of the observer, which is related to Clément's work on like kind of deployments of systems, binding of variables dynamically, and things like this. So again, there's lots of dimensions here in the kind of process algebra, kind of process spectrum, which still need to be properly explored and evaluated because it's not just one thing. Like bisimilarity finds attack, but lots of other things find the attack as well in different ways, and they mean different things for the attackers. Okay, and some are better for some protocols than others. So there's an interesting space of problems here. So there's impact for society here. We went through responsible disclosure. We notified ICAO in 2019, and essentially the way to mitigate this is to improve ePassport readers, make them aware, make sure that they don't have there's no possibility of holding the reader in a particular state for too long. This I'm not sure about who is actually responsible for that, because ICAO are kind of outside the law. They're the UN, and you can't sue the UN. So you can't go around telling every single manufacturer of ePassport readers, and so who's responsible is still something which we're not quite clear about. But we're working on that through the frameworks like GDPR. And this is their statement. And they have a word here only, which kind of is used to kind of soften the impact of what we do. But if you take out the word only, this is a very strong statement about the fact that they confirmed this is really an attack. Okay, so I'd like to leave this here, and you can read it in your own time, and pass back to Clément. So I think your sound's down again, just like earlier. Still not. No.
Can you hear me now?
That's it. We had this problem earlier, so yeah, probably the same thing. No, we lost you again. I've lost you anyway.
One, two, three. Hello.
I can hear you now. I can hear you now.
Ah, okay, sorry. I'm so sorry for that. Yeah, I blacked out for 2 minutes. I had an issue with my computer. I'm sorry about that. Thank you very much. I think
Okay.
you hit the perfect spot of accessibility and technicality. There was enough for people to get convinced that it was not an easy task to find this flow in the specification itself. And so I also enjoyed the fact that you were discussing the specification and not the implementations. I think that's an interesting point that you made across, and which makes a lot of difference. And it's interesting because on a different line of research, I'm actually trying to go the other way around. I'm trying to take the theory and to go more toward the implementation, but it's nice to see it go both ways actually.
Yeah, well, you can add more details about the implementation into the model. So for instance, if you add things like timeouts, you'll start to pick up on some of the practical attacks. So it's potential, that's yet another way you can go, is like timed equivalences for picking up timing side channels. So it's not a bad idea to actually build a little bit more detail in.
So yeah, okay. So
you see what I mean? Yeah.
The floor is of course open for question. I chat with Russ on a regular basis, so I'm happy to hijack the Q&A session, and keep chatting with him. But I have other chances. Well, you may or may not have other chances to chat with him. But just to reflect on what you were saying, to me, it's interesting too, because maybe not all, but many of the attacks I'm seeing actually exploit the default of the implementation and can't necessarily apply to the theory of the program that is under study. I actually taught a couple of those in compiler writing this semester, and most of them are, yeah, your program may be fine, but the compiler is going to mess it up if you're not careful about the optimization performance, that sort of thing. So I think it's interesting also to see the flaws in the specification itself. I also believe it's way harder to detect them, which is also why making your protocol and tool very interesting. So you mentioned it, but I don't think you shared any link or any name to that tool you developed in Singapore. So where can we find it? What is its name?
So the tool is called Spec, but the Spec tool doesn't quite solve this. So essentially, it's because the Spec tool hit the limit on this tool that I needed to improve the theory. Okay. On this particular problem, this class of problems. And this led to a kind of number of papers because it turned out that just inequality is really difficult. Inequality. So you have if then else, okay, in the else branch. Just evaluating the else branch symbolically gave rise to significant outcome. Essentially, it's because if you treat it classically, then it becomes like kind of non-monotonic, and then you have to do a lot of backtracking and so on. Whereas if you move to an intuitionistic setting, then you kind of get around this problem. So you start to use intuitionistic logic. And this allows you to kind of stay in a state where you don't know for as long as possible. So I don't know whether x equals y or whether x is not equal to y. And then only decide one way or the other as you need. And that use of intuitionistic logic makes your evaluation of the kind of state space really super lazy, and just takes you straight to the answer for a lot of examples like this. So really the insight here is that these open equivalences are somehow related to intuitionistic logic, and that allows you to improve the tool. And so the spec tool was based on open bisimilarity, which is essentially intuitionistic as well, but didn't have the inequality which you needed for these errors. The errors that were coming from else branches. So the tool, like you can download spec. You check which version because I think I left it hanging for like 5 years, and there might be a bad version. But there's a good version somewhere, someone needs to kind of basically take this new theory and actually build it into a tool like this. And the reason why that's a little bit difficult is because this problem with inequalities is also a problem in the underlying logic programming language which we use. Essentially, you're not allowed to write down clauses of a certain form where negation appears in a certain place, exactly in the place you need it for writing down these specifications. So we need to kind of start again with a new programming language, or you need to extend the logic programming framework underneath it itself to deal with more richer clauses. So there's a kind of a significant technical bottleneck there to overcome in terms of closing the tool so it matches the standard. So that's something interesting itself. So we touched on quite a few open research problems here, which can make it easier for other people to just write down the protocol and press a button and it says yes or no. That's ideally what you want at the end.
Okay. Well, thank you so much, Ross. I didn't see any question popping in any chat, but thanks a lot for wrapping up our colloquium semester. It was a pleasure closing it with you. I wish you a happy weekend, I guess. Thanks everybody for joining, and we'll resume the colloquium next semester in January.
Yep, and hopefully I'll see you in person before long as well.
That'd be nice. I would like that.
Okay.
Thank you so much.
Great. Enjoy your Christmas. Bye.
Bye-bye.